Hi, I'm Mike Ungerman of the Central Florida Computer Society. Today, we'll continue with the second in a series on electric vehicles. In our previous presentations, we've defined the various types of electric vehicles: hybrid EVs or HEVs, plug-in hybrid EVs or PHEVs, and battery-powered EVs or BEVs. If you've missed this presentation, be sure and review the recording of our first presentation to watch Dan Edmonds' very informative video of these types of vehicles. EVs are not a recent development. We might believe that using electricity to power a car is a recent technological development. However, around 1832, Robert Anderson is credited with developing the first crude electric vehicle. In 1884, this electric vehicle was built by Thomas Parker, an English inventor. It's obvious that we would not have electric-powered vehicles if we didn't have a means to store the electrical energy necessary to power them in a battery. Since the electric starter was invented in 1912, we have had a lead-acid 6-volt or 12-volt battery in our cars to run the starter of our internal combustion engine and accessories. Although early EVs may have been powered with lead-acid batteries, the standard for EVs over the past decade has been the lithium-ion battery. Here's a typical Tesla battery pack with its electronics. We have a guest lecturer today in that Dr. Billy Wu of the Dyson School of Design Engineering in the Imperial College, London, has authorized us to show his video on battery basics, an introduction to lithium-ion batteries. It has been abridged to fit in the time allotted. The full link is shown at the bottom of the video and is posted in my YouTube playlist at the end of the presentation.
Hi, I'm Dr. Billy Wu, and in this video I'll be giving an introduction to lithium-ion batteries, covering materials, key metrics, operating mechanisms, industry landscape, and the outlook for the technology. So firstly, let's have a look at why batteries are important. In short, portable consumer electronics such as mobile phones and laptops have been enabled through the ability to store energy in a compact and energy-dense way. The batteries in these devices generally have a capacity on the order of several watt-hours, where 1 watt-hour means you can discharge the battery at 1 watt for 1 hour, or 2 watts for half an hour, or half a watt for 2 hours. Next, there's an increased focus on the decarbonization of transport, where the internal combustion engine is one of the major contributors to global carbon dioxide emissions. In order to address this, many automotive manufacturers are now developing battery electric vehicles, where the battery size is of the order of approximately 10 to 100 kilowatt hours. Finally, we need to decarbonize the way we generate electricity, which goes into these electric cars. Otherwise, we run the risk of pushing the pollution problem elsewhere in the system. Renewable energy sources, such as wind and solar, are a good solution here. However, these are intermittent, and therefore there's a need for large-scale energy storage technologies to help buffer supply and demand. In this application, the energy storage devices are of the order of several megawatt hours. Now, when we talk about battery technologies, there's actually many different types, which we often characterize by their volumetric and gravimetric energy densities. As a point of reference, petrol has an approximate energy density of 9,500 watt-hours per litre and 12,800 watt-hours per kilogram. However, the efficiency of the internal combustion engine is generally quite poor. If we assume this to be 25%, then these numbers drop down to approximately 2,400 watt-hours per litre and 3,200 watt-hours per kilogram, which are still high, however starts to capture the whole system considerations. Now, as we mentioned before, there are a range of different battery technologies, with the lead-acid battery being one of the first commercially available ones. This was initially used to power things like milk floats and is still used today as starter batteries in cars. The nickel-cadmium battery offered an improvement to the energy density of lead-acid batteries, which enabled portable electronics. However, this chemistry was plagued by the memory effect, where if a battery is repeatedly charged before all its energy is depleted, it will memorize the decreased life cycle, and the next time you use it, you may notice a significantly shorter operating time. The nickel metal hydride battery again offered improvements in capacity to the nickel cadmium battery without the need for toxic elements such as cadmium. This technology therefore found its way into some electric vehicles such as earlier versions of the Toyota Prius. However, the real breakthrough in energy storage technology was with the advent of the modern-day lithium-ion battery, which typically consists of a graphite anode and a transition metal oxide cathode. This technology is the one which is powering your mobile phones and electric vehicles. Now, whilst lithium-ion is well established, many people are also researching next-generation technologies. This includes lithium metal anodes, where we replace the graphite with pure metallic lithium. The challenge here is preventing the major failure mode called dendrite formation, where shards of metallic lithium can cause internal short circuits. Here, solid-state battery technologies are being heavily researched as a solution. Beyond that, we have lithium-sulfur batteries, where the cathode has been replaced with sulfur, which has an exceptionally high capacity and low cost. And finally, metal air batteries such as zinc air and lithium air have long been researched as the ultimate solution for energy-dense batteries, but still suffer from significant challenges. Okay, so let's now focus on the lithium-ion battery and have a look at how this actually works. Here you can see a diagram which represents the cross-section, which you can visualize as having a structure similar to a roll of paper which is connected to the positive and negative terminals. If we then zoom into the cell, we can see it's made up of a number of different layers. First, we have a copper foil which acts as the current collector for the anode. Then we have a porous anode which is normally made up of graphite. On top of that, we have a microporous separator which prevents the anode and cathode from touching each other. Then we have a porous cathode which is made up of a transition metal oxide and a aluminium foil which acts as the cathode current collector. In each of the porous phases, we also have a liquid electrolyte which allows for the movement of lithium ions. When the battery is fully charged, lithium exists in between the carbon layers of the graphite. When the battery is discharged, the lithium becomes a lithium ion and an electron. The lithium ions can travel through the electrolyte towards the cathode. However, the electrons have to go around an external circuit where useful electrical work can be extracted. At the cathode, the lithium ions and electrons recombine and go into the layers of the transition metal oxide in a process called intercalation. When charging the battery, the opposite reaction occurs, moving the lithium back into the anode. This back and forth motion thus coins the term rocking chair mechanism, which represents how a lithium-ion battery works. It's useful to have a high-level perspective on the battery industry and supply chain. In the first instance, we have the raw materials with key elements including lithium, nickel, cobalt, and copper. Here, where the materials come from, can be important, and also how ethically these are sourced. Next, these raw materials are then converted into precursors needed for the active material manufacturing. Here, key considerations include what form of lithium precursor is used, i.e. a lithium carbonate or a lithium hydroxide. The processing method used also is important in terms of the quality of the material produced. Next, these active materials are then mixed and coated onto their current collectors to make electrodes. Here, the manufacturing conditions are critical for good performance. Then, these electrodes are made into cells with different form factors with a resulting formation cycle which can define their future performance. These cells are then taken by Tier 1 automotive suppliers or high-volume automotive companies and made into modules and packs with thermal management systems and battery management systems. Then, these are put into vehicles for the lifetime of their use, where the load profile and environmental conditions can define their performance. Then, at the end of life, when a pack has reached 80% of its original capacity, these can either be used in second life applications such as stationary energy storage or be recycled. Now, as we scale up batteries to the millions needed for electric vehicles, we also need to consider how these are made. In the first instance, we take the active materials of choice and then mix these together with conductive carbon additives, a polymeric binder, and a solvent. The ink is then mixed and coated onto current collectors, after which the electrode is dried to remove the solvent and then calendared or compressed to increase the volumetric energy density. These electrodes are then cut and stacked into the cell form factor of choice, and then the electrolyte is introduced with the cell then being sealed. This has to be done in dry room conditions in order to avoid undesirable reactions. Next, we need to charge the cell, as most lithium-ion batteries are assembled in their uncharged state. This has to be done very slowly in the first instance to form a good SEI, and we term this step of the process formation. Finally, these cells are integrated into a system with a thermal management system and a battery management system. Clearly, there are many steps in this process, and therefore there's still a lot of room for innovation in the battery manufacturing space. Finally, as we briefly touched on earlier, there are different form factors of cells we can get. Prismatic cells generally have a high degree of mechanical stability since they have a rigid case and are often used in applications such as phones. Cylindrical batteries again have good mechanical stabilities and generally are the lowest cost form factor due to ease of manufacturing, with these being used in power tools and many electric vehicles. The most common cylindrical is the 18650, which means that this cell has a diameter of 18 mm and is 65 mm long. Finally, we have the pouch cell, which in theory has the highest energy density of the different form factors, but has low mechanical stability due to the lack of a rigid case. This is often found in applications such as drones, where the energy density is even more critical. So, we can see that there are many considerations needed to make better batteries. First, we need to make sure we have the right chemistry, and this really is the foundation of performance and cost. Next, we need to optimize its microstructure, which relates to how the particles pack together. This can really define whether a cell has better power or energy characteristics. Cell design also has lots of room for optimization, with cylindrical, prismatic, and pouch cells possible options. And finally, we need to take these cells and put them into a battery pack with a thermal management system, battery management system, and enclosures. Thus, overall, this is a multi-length scale problem which needs innovations in fields ranging from material science to mechanical engineering. So, to summarize, lithium-ion batteries are increasingly more commonplace. There are many different types of batteries which are defined by their anode and cathode materials. With lithium-ion batteries, they work via a rocking chair mechanism where the lithium moves back and forth between the anode and cathode. The key metrics of interest are cost, energy density, power density, safety, lifetime, operating temperature, predictability, and recyclability. The industry landscape for batteries covers many different aspects from mining, chemical processing, electrode manufacturing, cell and pack manufacturing, integration, and recycling. Within the lithium-ion battery space, there is again a variety of different anode and cathode materials, with the most common anode material being graphite, but with a general move to graphite silicon composites and potentially metallic lithium. The most common cathode material is NMC, where the move is towards more nickel-rich chemistries. Key performance metrics include C-rate, capacity, and energy, where we looked at some datasheets and discussed the role of power and energy cells. And finally, we discussed the different form factors, which include cylindrical, prismatic, and pouch cells. So hopefully this video was a useful introduction into lithium-ion batteries, which covered the core principles of how they worked and key considerations.
My thanks to Dr. Billy Wu for his comprehensive tutorial on lithium-ion batteries. There's a lot of science and math in his presentation, but for many of us, some basic information we should all understand if there's an EV in our future. In my next presentation, I'll focus on improvements in battery technology beyond lithium-ion. Many improvements are under development now and will be produced in the not too distant future. Some of these technologies are actually now available in EVs that will be sold in 2023 and 24. As I researched YouTube videos supporting battery technology, I added them to a playlist to share with our viewers. This is an active list, including Dr. Wu's unabridged video, and they will update as I discover and add new ones. Feel free to browse them at your leisure. The address is https://bit.ly EV-batteries. That'll be a shortcut to get to the playlist.
Okay, great. Now I asked Bob Baxter to just do a short, because he's talking about batteries. Bob, tell me about batteries. What's happened to batteries in you?
So I have a 2010 Prius. It has approximately 125,000 miles on it. About 3 months ago, the service hybrid warning signal lit up. I had a local Chevron station reset the error, and they made it very clear they don't replace these kind of batteries. It's a specialized industry. The error stayed off for about 2 months. I had it reset, only lasted a week or so. I did some research and I found 2 companies, Green Tech and Green Bean. I contacted Green Bean and scheduled a tech to come to my house and replace the hybrid battery in my driveway. Very easy. Let me move this out of the way. The price for doing this was only $2,167, including sales tax and a quote unquote lifetime warranty, whatever that means. See if I can move to the next slide. It doesn't always want to move. Give me a moment. In order to do this, I had to clean out the back of the hatch area. Underneath this pad down here, if you can see my cursor, it's not very bright this morning. That comes out and you get down into the well, and underneath that is the tire. Oops, one part. And this is what it looks like when you get all the way underneath it. The brown structures in the middle are the bottom edge of the seat backs that are folded down, so he has full access to this space to work. And here he is. The one on the left is the one that came out of my vehicle. The one on the right is assembling the brackets across the back of it so that it can fit in. It's a healthy thing. I didn't ask him how much it weighs, but it's a healthy piece of equipment. And there it is. He's got it pushed in there. And there it is in place and bright and shiny. And it works. That's the main thing. Let me take a moment and mention a little bit about the controls that you see. This is the dashboard. On the left side, you have the standard, your gas gauge, your mileage, a cute little tool that tells you at any instant in time that you're moving what your gas consumption rate is. It basically has drive, neutral, and reverse, and park. On the other side, you see the hybrid system indicator. As you drive, a line will move from left to right. There is a setting that lets you get some extra power. It takes more gas. And as you back off of the gas, you're going down the hill, it'll drop back into here. As you apply the brakes, the line will move over this way, and you can see these bars in this simulated battery. As it is charging, they'll stack up towards the top. As you're driving, it goes down to the bottom. When the hybrid system goes out, that all disappears. There's just a blank space over there. You do get to see your mileage. There are various settings here, miles per gallon, and your current mileage, and how many miles you have left on your tank. So that's what I have to say. Back to you, Ron.
Okay, just unshare your screen then. That's great. So listen, that's really interesting. Why I wanted Bob to talk about this, we were talking earlier in the week and he was telling me about this, and I thought $2,000 to have your battery replaced in your Prius. They come right to your house. I mean, that's not bad. That's pretty darn good. I'm impressed. That's great.
Green beans, most of the United States.
Yeah, yeah. I looked up the company and it's that's pretty cool.
How to choose an ISP in the US and Canada. I'm Hewie Poplock. What's a good internet speed? 0 to 5 megabits per second. You can check email, streams music on one device, and you probably can do a Zoom meeting. 5 to 40 megabits per second. Stream on one device, and some others you could see. 40 to 100 megabits works for streaming HD video on a few devices and downloading large files. Above that, 100 to 500 megabits, you can do quite a bit. And of course, 500 to a gigabit or more works for doing almost anything. Speed tests. How accurate are they? Sadly, they're often not at all accurate. Sometimes an internet speed test isn't accurate because the method the service uses isn't great. When you start a speed test, multiple things occur. First, the client determines your location and the closest test server to you. With the test server in place, the speed test sends a simple signal, a ping, to the server and it responds. The test measures that round trip in milliseconds. After the ping is complete, the download test begins. The client opens multiple connections to the server and attempts to download a small piece of data. At this point, two things are measured: how long it took to grab the fragment of the data and how much of your network resources it used. If the client detects that you have room to spare, it opens more connections to the server and downloads more data. The general idea is to tax your internet connection and see how much it can do simultaneously. Next is the upload test. It's essentially the same process as the download test, but in reverse. Instead of pulling data from your server to your PC, the client uploads data from your PC to the server. Let's look at a few speed tests. First, we'll go to Google and type in speed space test. We get a blue box. We click on that blue box and we get a speed test. And this is the result we got from that test. Next, we go to speedtest.net. We run the test and this is what the result we got. Then we ran the same test, but from Ooklay's app, and this is the result we got. And then finally, we ran Frontier's own speed test, and this is the result. How to choose an internet service provider in the US and Canada. Let's look at the US first using highspeedinternet.com. This is the website. Let's just look down. It just gives you some information. You can search by any state, information about them. But to get the information you want to put in your zip code. Let's use mine to begin with. At the top is an ad, and then below that are the different internet service providers, or ISPs, in my zip code. Xfinity, Spectrum, Earthlink, Frontier, T-Mobile, Home Internet, and Viasat, and Suncoast Broadband. And you can see what their top speeds are for download. I'm using Frontier, and I can get up to 2,000 megabits per second or 2 gigabits. Let's look at the plans. It takes you directly to their website, the Frontier website. It does not give you an intermediary that makes money on it, although this website may get some click-through benefits. But you can see what service they have, and you can contact them for more information. Then they have a lot of information on their pages, of course. They're advertising their service. So you can choose any of the plans and then take a look at information about it. Let's go back to the first page and let's put another zip code in. Let's take one in Mesa, Arizona, for instance. Again, an ad at the top, and then there are just a few services that are available in Mesa, but Cox is one that has up to 1,000 megabits per second, or 1 gigabit. So let's take a look at their plans. Takes you again to their page. And it gives you various plans that they have available. Now, they may not be all available at your address, and so you do have to put that information in, and then they will tell you if you have certain services available for that area. So that's highspeedinternet.com. How to find an internet service provider if you live in Canada. Saying that the highspeedinternet.com is only for the US, I looked for a similar website for Canada. Came across a couple. This is the one that I chose to take a look at with you. And it's called Whistle Out. It wants here, instead of a zip code, a street address. But let's take a look down here a little bit more. There is some information, some news. Again, a list of providers in the various areas, and then choose the right internet plan. In other words, some information on how to do so. And then it lists the major companies in Canada, and you can click on any of those and go to their page as well. But let's come back up here to the top, and let's go ahead and put in an address in Comox, British Columbia, and we search. Just like highspeedinternet.com, it gives us a list of various companies that are available in that area, and a little bit different. They give some of the pricing right here as well at different speeds, and you can come all the way down towards the bottom and get more results and get faster and faster speeds and load more results, and we get more. And there's one that you can get up to 2,500 megabits per second, or 2.5 gigabits. Let's take Shaw right here, this one. They call it Fiber Plus Gig. It tells you that it's $99 a month. And it gives you information on the speeds and what the upload speed will be as well. And then some extras. So it gives you a lot of information for you to decide which service you want wherever you are in Canada. Now let's go back to the internet here at Whistle. They do have some sections that you can look up as well. Best internet for Zoom. Check your internet speed so you can test your internet speed directly from this website as well. Not very accurate. I wouldn't go by that. So that's Whistle Out for Canada. They also have cell phones and some iPhone details if you want to take a look at that as well. How to choose an ISP in the US and Canada. I'm Hewie Poplock.